Hello everyone, welcome to my channel. I am Dr. V. Jayakumar. I make lecture videos for the benefit of mechanical engineering students. Having studied about the basic concepts of degrees of freedom in our earlier video, we will solve numerical problems on determination of degrees of freedom or mobility of different planar mechanisms using Kutzberg criterion in this video. So let's get started. In order to determine degrees of freedom of planar mechanisms, we are going to use Kutzberg criterion that says that degrees of freedom is equal to 3 into n minus 1 minus 2 into L minus H, where n is number of links of that given mechanism, L is equal to number of lower pairs. Number of lower pairs is equal to number of binary joints that mechanism has. So in other words, I could say L equal to J. H means number of higher pairs that mechanism has, right? So this is the equation we are going to use to solve all problems in order to determine degrees of freedom of the given mechanism. If the degrees of freedom is equal to 0, that means that the mechanism forms a structure. If the degrees of freedom is less than 0, say minus 1, minus 2 and so on, then the structure is statically indeterminate structure. If degrees of freedom is greater than 0, say 1, 2, something like that, then we can call the mechanism is having constrained motion. These theoretical concepts we have already discussed in our earlier video. Right, we are going to solve 10 numerical problems in this video. But what I would suggest is you could pause the video and try that problem whether you get the answer correctly or not. Else you can start solving along with me. Shall we move on to the problems? Yes. This is the problem number 1. Determine degrees of freedom or mobility of the given mechanism below. We know that we are going to use Kutzberg criterion for all problems. Right. Before solving the problem, first we have to know the number of links that mechanism has. So let us name them. The thumb rule is let us start the numbering from the fixed link. Here, fixed link is indicated in 3 places. All of them should be number 1. They are not different links. All fixed links should be numbered 1, right? Yes. Now we can call this is link 2, link 3. Now here what we have might look like 3 different links. They are not 3 different links. That is known as ternary link. Ternary link is nothing but link that has 3 nodes. So this is link 4. Now we could call link 5, 6, 7. Number of links is equal to 7. Next, we need to determine number of lower pairs, which is equal to number of binary joints. I will denote binary joints by circle. So link 1 and 2, we have one binary joint. Here I have one. Here it might look like it forms the ternary joint. They are not. This is not ternary joint because 4 is a single link. So link 4 and link 3. So it is also a binary joint. Do not get confused as if it is a ternary joint. Okay. Now 4 and 5 binary, 1 and 5 binary, 4 and 6 binary, 6 and 7 binary, 7 and 1 binary. So calculating them, I will have 1, 2, 3, 4, 5, 6, 7, 8. So I have J equal to 8. Just by going through the diagram by visual inspection, can we find any higher pairs here? Is there any 2 links are having either line or point contact? No. So in this case, H is equal to 0. There is no higher pair. So hereafter, mere substitution in the formula, I would be getting the answer. So by substitution, I get degrees of freedom for this mechanism as 2. What it indicates? The degrees of freedom is equal to 2 implies that we need two separate inputs that are to be given to this particular mechanism. Then only we will be getting constrained motion from this mechanism. Clear? Right, let us solve numerical problem number 2. As always, let us determine the number of links first. Let me go for the fixed length 1, 2, 3, 4, 5. This slider 1 is number 6. Okay. Number of links n equal to 6. Now let us find number of binary joins. One binary here, one binary here. Here we have sliding joint, which is again a binary joint. And also between 5 and 6, we have one more binary joint here. So we have 1, 2, 3, 4, 5. 5 binary joints. Plus we have here one ternary joint. So one ternary. We know that one ternary equal to two binary joints. Therefore, I could find J is equal to 5 plus 1 into 2. So J is 7. Is that clear? Right. So is there any number of higher pairs here? In this problem, there are no higher pairs. So H is equal to 0. So substituting them, we will be getting the answer. That's it. Problem number 2 is done. Now we will see problem number 3. So fixed link 1 here, 1. Now this entire link might look different, but it forms a single link. So I need to call this entire link as link 2. Same is the case here. The entire thing is link 3. This is link 4. This is link 5. So I could say number of links as 5. Now let us identify what are the number of binary joins. It forms one binary joint, 1B. Is it a ternary or binary joint? It is not ternary joint because it is one link. Link 2 is a single link. So here we have one binary only. This also might look like ternary. It is not a ternary. It is a binary. Same here. All binary in this case. So counting them, you will be getting 6. Is there any higher pair? So easy. There are no higher pairs, no point contact, no line contact, and hence H is equal to 0. Substituting them in this formula, we will be getting the answer. So degrees of freedom equal to 0. That means this mechanism forms a structure. The same way we can do problem number 4. First naming, all fixed links are 1, 2. This is ternary link, ternary link, ternary link. 6. This one 7. We have one more here, 8. N is equal to 8. Here one binary, it's not ternary, it's a one binary here, one binary there. It might look like a quaternary joint. It is not, because 3 is one link, 4 is one link. Only 2 links are joined at this joint. Therefore, this is a binary joint. One binary, one binary, one binary, one binary. Count them. I am getting 10. Is there any higher pair? No. So substitute them. We will get the answer. So we get degrees of freedom is equal to 1. That means we need only one input motion to actuate the mechanism, which will give us the constrained motion. We'll move on to problem number 5. Again, this is fixed link. Can you call this ternary as link 2? No. In this problem, this ternary link itself fixed. So it forms one link only. So we have number of links as 8. Now let us find number of binary and number of ternary joins. First we'll go for binary. One binary. Yes, binary or quaternary? One binary, one binary, one binary, one binary, one binary, one binary. What about here? This is not binary. Here we have links 5, 6 and 7 are joined at a single joint. What is that name? That name I'm denoting by 2 circles. That is one ternary joint. Same here as well. I have links 2, 3 and 5 are being joined at the single joint. So here also I have one ternary. So now I could find equivalent binary joints, which is equal to number of binary joints 1, 2, 3, 4, 5, 6, 7 plus how many number of ternary joints? 1 and 2. 2 ternary joints multiplied by 2 because one ternary joint is equal to 2 binary joints. We know that. So we have totally 11 equivalent binary joints in this mechanism. Of course, there are no higher pairs in this problem. So substituting them, we will get the answer. There you are. This problem we are getting degrees of freedom as -1. What it means? It means that it forms statically indeterminate structure. Such kinematic chains will be useful while designing the clamping mechanisms. Okay. Now let us get on with problem number 6. Shall we give the link name? This is one fixed here one fixed. This is cam which rotates link 2. This oscillating follower is link 3. Here it's very important to note that it is welded. This roller and this link are not different. So there, this lever as well as this roller put together form link 3. If in your problem, if they have not mentioned that it is welded, then we have to represent roller as an individual link, link number 4. Is that clear? Therefore, number of links is equal to only 3. Now let us find number of binary joints. So here we will have one binary. Here we will have one binary. Since it's welded, we will not have binary here. Okay. So only we have 2 binaries there. What is this type of joint? This type of joint is higher pair joint because it has point contact or line contact. Therefore, in this problem, we have h is equal to 1. Substituting that value, we will be getting the degrees of freedom value. So we get degrees of freedom is equal to 1. Shall we solve problem number 7? As always, let us number the fixed link first. Fixed links are shown at 4 places, so all should be named as link number 1. This is 2, 3. This slider 4. This link has 5. So this is 6. we have 7 and 8. Therefore, number of links is equal to 8. Now here we have one binary, one binary, one binary, one binary here, one binary there, one binary, one binary. This place is what we have to be careful. How many links are joined in this point? We have link 3, link 4 and link 5. That joint is one ternary joint. Very interesting. In addition to that, link 1 and 4 form sliding joint. So that means we have one binary. So that place is very crucial where we have one ternary as well as one binary. Is that clear? Yes, we have 8 binary plus how many ternary? 1 ternary. So 1 into 2. So we get 10 equivalent binary joints. Now easily we can find the value. So this mechanism, we have only 1 degrees of freedom. Now let us solve problem number 8 in the same manner. First, numbering of the links. Obvious. So number of links n equal to 7. Now let us see the binary joints. 1 binary, 2, 3, 4, 5. It's a binary or ternary? Binary. 6, 7, 8. So we have 8 binary joints. Here we have higher pair joint because it forms a point contact. Therefore, so substituting them, we will be getting the answer. So we are obtaining the answer as 1. Shall we move on to problem number 9? Let us name the link 1. Here we must understand that this entirety is one link. Therefore, we can call that as link 2. Same way, from this to this is link 3. So similarly, I could call this link 4, link 5, then link 6, link 7. We have to call it as link number 8. Slider is link number 8, therefore n is equal to 8. Now here we have one binary between 3 and 8, and also here we have one sliding as well. So one more binary. So here I have 2 binaries. So let me count them. 1, 2, 3, 4, 5, 6, 7, 8. Here 9 and 10. Therefore, there are 10 number of links. Of course, there are no higher pairs in this mechanism. So degrees of freedom for this problem is 1. It's a final problem. This problem exactly the same to that of the previous one. So number of n is equal to 8 as in the previous problem. Now let us find number of binary joints. 1, 2, 3, 4, 5, 6, 7, 8. Here we have 1, 9. So number of binary joints are 9. Here we have roller. What is that? It means we have one higher pair. Sliding joints and roller joints are different. In this previous problem, we had sliding joints, hence it is a lower pair. It comes under binary joint. Whereas here, it is a roller joint. When we have a roller, it comes under higher pair. Therefore, H is equal to 1. Now I could substitute in the formula 3 into. So for this problem, we are obtaining degrees of freedom as 2. Hope you have understood all this problem clearly. If you found this video useful, like this video, share it to your friends, subscribe the channel, and also press the notification bell icon. That's it. Thanks for watching. Take care. Bye.